In module 6, we are going to talk about general block designs. As a matter of fact, this is the module which will give us a taste of what is taken up in postgraduate department. So long, whatever we take up are mostly in some form the material covered in undergraduate course. But from now onwards, we will be having a taste of the topic in its most general form. So we will start with the block designs, then we will pass on to row column designs, and eventually we will go to factorials and all that. Okay, so let's see what is in store for us for a general block design involving one single blocking factor. Therefore, we have got blocking effect and the treatment effect in the model. I am eager and happy to present before you the general concept of block designs. So there are plenty of real life examples of experimental situations admitting formation of natural blocks which in a way provide a classification of seemingly heterogeneous experimental units into homogeneous groups. That is what we call the blocking factor. This is all accomplished before administering the available treatments on the experimental units. The expertise of the field operations manager is to focus on blocking and then making sure that the blocking is implemented in the experimental field. The liberty, commitment, responsibility of the experimenter or the design theorist is to provide adequate allocation of the treatment across the experimental units in different blocks. Needless to say, the term adequacy has to be understood well.
Sir, thanks for introducing the concept of blocking. I am tempted to reiterate what you said, but in a slightly technical manner. There are n experimental units, but not all are internally homogeneous. There is one blocking factor having B alternatives, and for the jth alternative, there are kj experimental units. In design theory terminology, we say that we have a block design with B blocks and the jth block being of size kj, so that n is equal to sum over j kj, which is equal to total number of experimental units under consideration. Now, as before, we have a set of V treatments for comparison of their effects. In a given experimental situation, to start with, we are given the design parameters, which are N, B, K1, K2, KB, and V. Now, our task is to administer the treatments across the experimental units. So, may I continue further?
Yes, go ahead.
So let Nij be the number of experimental units from among those in the jth block receiving the ith treatment, and I is equal to 1 to V and j is equal to 1 to B. Clearly, here Nij's are greater or equal to 0, and sum over I Nij is equal to Kj, and where j is equal to 1 to B. Now at this stage, it seems logical that we introduce a matrix notation. So let us introduce it. Let capital N be the matrix with elements Nij, and it is a V cross B matrix where V represents the treatments and B represents the blocks. So it's a B cross V incidence matrix. Here Rij is equal to sum over j Nij, and which represents the replication of the ith treatment, where as we know I is equal to 1 to V. Also here R is a vector of the elements R1, R2, Rv, and it can also be called as a vector of replication numbers, and K is equal to this vector which contains K1, K2, Kb. So vector of block sizes it can be think of, and here is the RD. Those are the diagonals of R1, R2, Rv, and K1, K2, Kb.
Yes, you are writing RD,
Huh. Yes,
D
sir.
on the front and then KD.
Yes, so
There should be a
then,
consistency of notation.
yes, type,
It is
yes.
better to put D on the top to mean diagonal. Okay.
Yes, sir. Now, sir, I'm tempted to mention that the incidence matrix, capital N, of order V cross B, as we have mentioned earlier, possesses the entire design layout, and these should serve for a study of the theoretical aspects of the design, while the same combined with the experimental data, generally denoted by a vector y, will provide the basis of a data analysis.
You are very right. We can now introduce the fixed effects additive model involving the block effects and the treatment effects in the most general form as we have envisaged. Remember, for the ij combination, nij is the number of experimental units allotted to the treatment I in the jth block. So provided nij is positive, because it could be 0 as well, as you said. So provided this is positive, we may denote the experimental observations specific to this ij combination as yij as a vector, yij1, yij2, dot dot dot, yij, nij. So that whenever nij is positive, I know there are so many observations, experimental units corresponding to the combination ij, therefore so many observations have been generated. Now we adopt a fixed effects additive model. So this yijk we model as mu, general effect, tau I, the effect of the ith treatment, beta j, effect of the jth block, and the error, with the usual interpretations of the fixed effects and the assumptions about the errors. At this stage, it is worth recalling our purpose in this experimentation. Notwithstanding the possibility of differential effects of the blocks, our primary interest lies in testing if there are differential effects of the treatments under consideration. That is our primary target.
Yes,
In effect, therefore, we want to test the null hypothesis tau i's are all equal. This testing problem presupposes our knowledge about all pairwise treatment effects differences to be derived from the data arising out of the chosen design. But whenever we say tau i's are all equal, that amounts to tau 1 minus tau 2 equal to 0, tau 1 minus tau 3 equal to 0. All pairwise differences
Treatment
we are
contrast.
testing equal to 0. To test that, we need to have estimates. It presupposes that all pairwise treatment effect differences are being estimated from the data. A design may or may not possess this feature of what is termed treatment connectedness. The concept of treatment connectedness means for a block design, connectedness refers to the property of treatment connectedness, which means that all treatment differences can be unbiasedly estimated from the data arising out of the design. For a given design, one simple way to check this is to verify the chain definition of connectedness, a concept due originally to R.C. Ghosh. Also, there is a latter technique by Park and Shah. Their technique of formation of what is called treatment connected equivalence group is also worth mentioning.
Okay.
This seems to resolve the problem of verification of the property of connectedness almost instantly for any block design.
Sir, I think I can guess what you were up to in terms of equivalence group. If two different treatments, I and I prime, are present in the same block, the corresponding observational difference provides an unbiased estimate for the treatment effect difference, that is for tau I minus tau I prime. Right, sir? So in that case, from connectedness perspective, we may say that the two treatments are connected and hence belong to the same equivalence group.
Very good. So what you are saying is that if there are two treatments in the same block, if we take their model expectation and we take the difference between the two, mu will cancel out. beta j, if it is in the jth block, beta j will cancel out. What will remain is tau I minus tau of I prime. Therefore, the difference will be estimated by taking the difference of the corresponding observational contrast. I think that is what you are saying.
Yes, sir,
So
absolutely.
you are saying that from connectedness perspective, we may say that the two treatments are connected and hence they belong to the same equivalence group. So within every block, all the treatments they form an equivalence group.
So obviously then from each block we can go on forming equivalence group of treatments as you have said. Now again, if one treatment is common between two different equivalence groups arising out of two different blocks, the groups can be obtained and the larger
They can be combined.
yes sir, and a larger equivalence group can be formed.
So if there is any treatment which is common to two blocks, through that common treatment,
They are
the two
connected.
groups can be merged together.
Yeah.
And we can have a bigger equivalence group. Okay.
Yes, sir. And we continue like this and verify if all the V treatments are involved in this process in one single equivalence group.
Very good.
That should define our treatment connected design, I believe. I can see that when this holds, all treatment effects differences are unbiasedly estimable. So I am almost tempted to say further that in such a case, all block effects differences are also likely to be unbiasedly estimated. I mean, this chain definition and single chain formation rule also applies to block effects. Am I right, sir?
Yes, SG. Do you mean to say that a block design is treatment connected if and only if it is block connected? Can you go that far?
Yes, sir. I'm pretty sure that is true. Obviously, that's because I can reverse the roles of treatments and blocks. I think I can elaborate on my claim.
Very good. That is indeed true, and you are almost there. As you see, it is only natural that we should deal with connected block designs because connected block design should give us a chance of estimating all treatment differences, and that is a prerequisite for testing the null hypothesis of equality of all treatment effects. So therefore, we should deal with a connected block design. So do you realize that this calls for a minimum number of experimental units across the blocks? Here is a quiz for you. Imagine there are 10 treatments to be compared and there are only 3 blocks. For a connected block design, do you need any condition on the block sizes K1, K2 and K3? There are only 3 blocks, but there are 10 treatments to be compared. As you know, within a block, all the treatments will be forming an equivalence group. But to be connected, all the treatments should form one single equivalence group. So I should borrow from this any common treatment between blocks to enlarge the group. If that is the case, then I need a condition on the block sizes K1, K2, K3. So that's the kind of thing I'm talking about. You need a minimum number of experimental units across the blocks to be able to tell about the connectedness of the design.
Yes, sir.
So that is where I think I can stop, but you can sense, imagine K1 equal to K2 equal to K3 equal to 3. That will not be enough. That will not give enough degree of freedom to you to incorporate all the 10
treatments.
I can take 3, 3, 3. That means it only takes care of 9 distinct. So not even all the 10 are accommodated. If I take 4, 4, 4, there are 12. So yeah, I can accommodate all the 10. But if I fail to accommodate any common treatment between 2, then they become disconnected. So there are issues like this. We need to know what should be K1, K. So depending on the number of blocks, how many observations are we talking about to make it connected? Like this, there are interesting problems. Some such problems you will see in the questions and in the MCQs as well. While I started thinking about the exercises in this module, I thought let me give more emphasis on our understanding about connectedness in a block design, various forms of tackling the problem, talking about the sample size, talking about the block compositions, because as you know, connectedness is the most important concept for us to be able to go ahead with inference. So that is the spirit of the problems that are set in this exercise as well as the MCQs that are coming up here. All kinds of connectedness notions. Okay, question number 1 reads like this. In a block design, there are 6 blocks and you are given the block sizes 3, 4, 4, 4, 5, 8. Note that the statistician has no control on these block sizes. They are just coming out from the experimental conditions. That there are 6 blocks is not your choice. That the block sizes are 3, 4, 4, 4, 5, 8, that's not your choice. You know how many treatments you want to accommodate, but you have to be able to accommodate in a way that you admit that there are block differences and that you want to estimate the treatment contrasts. So your goal is very specific. Imagine there are V treatments to be compared for their differential effects. What are the lower and upper bounds on V so that this problem can be resolved? That means so that we can get a connected block design. Give explicit examples of block designs for each case. For every choice of V, where you think that the problem can be resolved, you can generate a block design, connected block design, give the solution. V equal to this, it exists, here is the solution, etc., like that. You have to do it for all possible choices of V that are admissible. So that for the lower bound to V, it is possible to carry out an ANOVA test for the relevant hypothesis. So you are only told about the smallest value of V. For V equal to this thing, this is the smallest value, for which you can get a connected block design, display the connected block design, and argue that you can carry out an ANOVA test for the relevant hypothesis of equality of the underlying treatment effects. Also argue that this is not possible for the upper bound unless ... So what is the condition needed to show that even for the upper bound on V, it is possible to estimate the error, to go for testing the hypothesis of equality? This is a very good problem, conceptual, particularly the last part, fill up the blank statement, unless what? That is something that a student should ponder about. Okay?
Okay, sir.
The second question is, there is a block design with V blocks and each block is of size k less than V. The blocks are all of equal size, that is k, less than V, where as usual V is the number of treatments. Deduce conditions on the design parameters B, V and K. All you are given is that there are so many blocks. The blocks are of constant size k, you know k, you know how many treatments you want to accommodate. These are called the design parameters B, V and K. Deduce conditions on the design parameters so that a connected design is hard to construct. Give a condition for which it is impossible to construct a connected design. I can take B equal to 10, K equal to 3, V equal to 100. It's an absolutely hopeless case. You have to think of conditions on BVK so that a connected design is hard to construct. But that example people will not buy. B equal to 10, K equal to 3 and V equal to 100. People will say, are you kidding? Is that a good example? No. You have to come up with a convincing example to show that you are narrowly missing connectedness property. Okay?
Yes.
That's the kind of thing. Question number 3. Start with a connected block design with parameters B, V, K1, K2, KB. That is again very interesting. You know how many blocks are there. You know the block sizes. You know how many treatments you can accommodate to have a connected block design. And you already have a connected block design with you. Suppose one observation is missing from somewhere. Would the design still remain connected? Give examples of possible situations.
Okay.
The answer is yes or no. It will remain connected or it will not remain connected. There cannot be any third choice.
Option.
So give an example where it will be connected. Give an example where it will not be connected, even with one observation missing. These are the two cases you are supposed to take up. Next one is, a block design is connected and it has already incorporated exactly V treatments. Good problem. So you know the block sizes, you know the design, and the design you can verify that it is connected and it has incorporated V treatments. Can it still entertain one additional treatment and remain connected? So from V I want to extend to V plus 1. Can I just put into somewhere, because I am tight on the blocks and the block compositions. If I have to incorporate one more treatment, I have to take out one and plug that one, because there is no extra block size coming up. It's not that you increase k to k plus 1. That is not the issue.
Not possible. Yes.
Okay, these are all given. You only take out one and put the new treatment. Give examples of possible situations where, by incorporating the new treatment, the design for V plus 1 is also connected or it is not connected. Give both types of examples. So these are the 4 questions that I have over here, all relating to the issue of connectedness, basic understanding, etc. Can you take up the MCQs now?
Yes, sir. So here is the first one. A connected block design will remain necessarily connected if one treatment is deleted from the entire experiment. So the 3 of the options are the statement is always true. The second option is the statement is always false, and the third one is it may be true or false.
It depends.
It depends.
Okay.
So these are the 3 options.
Okay.
The second question is a disconnected block design will be connected by addition of block of treatments, and so fill up the blanks, and
Right.
the options are a suitably
Composed
composed block of treatments, an arbitrarily block of treatments, 2 arbitrarily composed block of treatments. So which one will
So
be
let's try
there?
to understand. A disconnected block design. So to start with, the design is disconnected. What does that mean? The treatments cannot be put together in one single equivalence group. So you have patches of treatments. These are the treatments in one group. These are the treatments in another group and
one.
so on. So they are kind of separated. But now I want to make it connected. So I have to add something by addition of a suitably composed block of treatments, an arbitrary block of treatments, and 2 arbitrarily composed block of treatments. These are the options.
Yes.
Okay.
And the third one is a connected block design involves V treatments in B blocks.
Okay.
Another disconnected design involves V star treatments in B star blocks.
Oh, one is connected, other is disconnected.
The
Okay.
second one is disconnected. And the composition of the 2 designs comprises of B plus B star blocks.
Okay.
This composition will provide a connected design if option A is V star treatments from a proper subset of V treatments.
Okay.
Option B is V treatments form a proper subset of V star treatments.
Okay.
Option C is V is equal to V star.
Okay.
And option D is none of the above.
Bah,
So
very interesting.
these are
Okay.
the 4 problems.
So you have one connected design, another disconnected design.
design.
This involves V treatments, this involves V star treatments. You don't know what is what. Now one option is V star. They form a proper subset of V. So if there are 10 treatments there with a connected block design, you have 3 out of them forming a disconnected design. You are combining the one blocks and you want to know what is happening. Or is it that V is a proper subset of V star?
V star.
Is it that the 2 are equal or none of the above? Very interesting. Okay. This is relating to connectedness.
Yes,
Is that
sir.
all? Okay.
Yeah.
So to sum it up, we started by a general description of a block design wherein the number of treatments is arbitrary, the number of blocks is arbitrary, and corresponding to a combination of treatment and block, we can have either none or any number of observations attached to that particular treatment within that particular block. It's a very general concept, and thereby you introduce the concept of incidence matrix of the design, which is the treatment across block incidence matrix. Through that, you visualize the observations, you build a model on that, you bring in the concept of treatment connectedness and block connectedness. Treatment connectedness means all pairwise treatment differences can be unbiasedly estimated from the data and from the model. Block connected means all block effects differences can be unbiasedly estimated from the data and the model. And we tried to argue that in a block design, treatment connectedness implies and is implied by block connectedness. To verify treatment connectedness, we use the fact that within every block, the treatments, the distinct treatments, they are all connected together. That gives a concept of formation of chain, and we apply the chain rule to form bigger and bigger chains by looking for common treatments across different blocks. And then we bring in the concept of treatment connectedness, when the equivalence group, it entails all the V treatments together in one single equivalence group. So therefore the verification of treatment connectedness is almost immediate in a block design. That is the comment made. Then we talk about the necessary and sufficient condition for formation of connected block designs for given design parameters, namely number of blocks, number of treatments, and the block sizes. So there are many interesting issues here. What if a design is connected and something is missing? What happens to the resulting design? What if there are two designs and they are put together in terms of the connectedness of the design? All these issues are there, and these are taken up in some of the exercises and MCQs. I hope the students will like this way of understanding the basic properties of block designs. We have yet to take up the analysis, which is a highly non-trivial exercise in the context of this kind of most general block design setup. So we will now take up a study of the analysis of a connected block design in its most general setup under a fixed effects additive model. Therefore, in the ANOVA, we should have the block degree of block connectedness, treatment connectedness, and the error and the total. We should know what are the different components of sum of squares, how to compute them in a very general setup. So these are the things which will come up in our next module. So first we talked about the combinatorial properties. Now we will go for the analysis aspect of a general block design. That is coming up in module 7. Thanks for your attention.